My name is Thorsten Schütt. I'm working for the Zuse Institute in Berlin, and let's start with the usual talk on scaling web applications. You often find these talks. So we had this really cool idea for our web application, and we had an Apache and some business logic and a MySQL server on this one box, and nobody really cared, but it was working. And then suddenly somebody got interested in our application, and we had to add more machines. So the first step is splitting it into two machines, one for the SQL server, one for the web server. Then you get more users and more users. You go to several web servers and one database server. You get into a group of SQL server where you have one master server and some slave servers for replication. So you're usually doing this for more performance and for reliability, because now you don't have a single point of failure anymore. You get more performance out of your system, and it seems to be working. So the fifth step is you have these group of small clusters of database servers. You start to partitioning your database into these groups. You can add more clusters as you go. You have some directory which tells you to which cluster to go for which kind of data. And yeah, you have a couple of hundred Apache servers in the front. You can add something like caches, like web cache or so. But usually the talks stop at this point, because most of the people are happy with this scenario, but nobody really knows what is the next step. So there are some ideas what you can do. So the first three are into the peer-to-peer direction, where you use a peer-to-peer overlay for your database. MySQL cluster is kind of similar, but more tightly connected. Or you try to do offline computations. So you have a job running which creates a new data structure for you, or index structure, and then you serve your data from there, like we saw with Google Maps. So you have a job which creates the maps, and then you serve these created data sets. And yeah, one other approach would be Google File System. Now, we want to go into the first direction. We want to get the peer-to-peer systems into the data center, because they are designed for scalability. They are designed for repairing themselves, and usually you don't have to take care of the system, it repairs itself. So what we have is a peer-to-peer overlay at the bottom. We have replication for failure tolerance. We implemented transactions on top of it so that we can actually use it as a kind of a database. And yeah, the demo application is Wikipedia at the top. So the first step is the peer-to-peer overlay. Who of you knows what a DHT, a structured overlay, or chord is? Okay. You get a 3-minute break, because chord sharp is basically chord without the hash function. For the rest, chord sharp, you can see it as a dictionary. We support 3 basic operations. You can insert a key value pair. You can delete a key value pair. Or if you know the key, you can make a lookup and get the value back. And yeah, chord sharp is a distributed version. You have a list of key value pairs. You somehow split it up over several nodes, and together these nodes will implement this distributed dictionary. So first you define what kinds of keys you will support. In this case, we have strings. Every node picks a random identifier from your key space. In this case, I picked Turing Award winners. And then the nodes will form a large ring. So each node has a connection to the next node with the next higher identifier. So in this case, Bacchus will have a pointer to Cod, and Cod will have one to Dijkstra. And so you build this large ring. And this is basically your structured overlay. Now you want to store data in this system. So when you have an item, you go to the node, which is in clockwise direction the first one you encounter. So when you want to store that Alan won his Turing Award in 2006, you go on the ring, and the first node you will find in clockwise direction will be Bacchus. So you store on this node this key value pair. And the same for Thompson, Bach, Beckman, and Clark. So now you can go to one of the nodes and ask him, let's, for example, you go to Wirt and ask him, hey, what is the value for Alan? So Wirt will tell you, oh, I have no idea, but we can forward the request to Yahoo. And Yahoo will forward the request to Bacchus, and eventually you will find a node which is responsible and gives you an answer back. But unfortunately, it's a ring, so you have to go n divided by 2 steps on average, and that's way too slow for large systems. So you add more pointers to the system. And here the idea is you put log n pointers on each node, and you make them exponentially spaced, so that with greedy routing you can end up with log n hops. So the base of the logarithm is 2 in this case, but you can increase the size of the state, and you will can basically choose the base of the logarithm. So if you say, well, logarithmic routing is not that great, I would like to have a base of 32. In most cases, your system will be so small that you can route in 2 hops on average. So what we are doing here is we fill this routing table. The first pointer will be to your successor, and then you ask your successor for his successor, so you get a pointer of length 2. Then you take this pointer of length 2, go to the node and ask him, hey, do you have a pointer of length 2? Yes, I have. So then you get a pointer of length 4. And so recursively you can build up your routing table, and they are exponentially spaced. And the length increases by a factor of 2 with each step. And it doesn't really matter what kind of distribution you have. So in this case, we can have range queries and everything. With the usual hash tables, they assume that you have to hash your data, and then you get an even distribution of items, and then you can play some tricks with the routing tables. But this formula is completely independent of the key space distribution. So now we have this distributed hash table, which is completely decentralized. Every operation is only based on local knowledge. You have very simple algorithms which can repair your system when new nodes join the system, when some fail or leave the system. For example, if you see that your system gets overloaded, you can get a new rack of machines, start up the software on these nodes. They will join the ring. The ring will repair itself, and you get the additional capacity of the new nodes. In a moment, I will come to load balancing, and the load will be evenly spread over the new nodes and the old nodes, and you get more capacity. The system supports range queries, but we are not using range queries here directly, but in a more indirect way, but I come to that in a moment. So the problem with DHTs is you can't really use them, because when you want to update items, you can go to the node, but there can be slight errors in your overlay, and you think that this node is responsible for the item, but actually he's not. Or there are maybe 2 nodes thinking that they are responsible for this item. So we introduce replication and transactions, and it will solve some of the problems. Yeah, as I said, high churn rate can get you in trouble with consistency and failure detectors. So the classic example is that you have a banking account. You want to withdraw 100 euros from the first account and deposit on the second one. But as we have replication, you're actually doing an operation on 6 items in this case, if your replication degree is 3. So we have a transaction scheme based on Paxos, which gives you the possibility to execute these transactions, and you will have consistent data updates. Every transaction will have a group of transaction managers. You can decide how large to make this group, and a couple of items, of data items will be involved in the operation. So the leader is elected among the transaction managers, and he will coordinate the transaction, but if he fails, one of the other transaction managers can take over. And yeah, the protocol, you start with doing a lookup with a normal logarithmic routing for the items and the transaction managers. They will report back to the leader who's involved in the transaction. Then you tell all the participants in the transaction, these are the transaction managers, these are the items involved. So the first round is with logarithmic overhead, but all rounds from here are using direct communication. So the first two steps are kind of expensive, depending on how much state you're willing to dedicate to routing tables, but the rest is pretty much not for free, but the latency is much smaller. Then the items will check whether they are able to execute the transaction or whether something else happened concurrently, and will tell the transaction managers whether they think that they can execute this transaction. And at this moment, they will lock the items so that no other transaction can happen concurrently. Then the transaction managers together will notify the leader whether the transaction will be successful or not. And then the leader will tell all participants that they can commit the data, release the logs, and basically finish the transaction. This leader and transaction manager concept is necessary because we assume that nodes will fail, and we don't want to have logs on items which will never be released, because then you can't do anything with your data anymore. And the algorithm depends on that more than half of your nodes will survive the complete operation. So usually you don't find transactions in DHTs, but they're necessary to update several items and their replicas at the same time without getting into consistency issues. And for those of you who have programmed with DHTs, it's really a pain in the ass to get this. You send a message, please update this item, and you don't know whether this other node is still alive or whether he's just slow. And should I send this update operation again, or should I wait a little bit longer? So with the transactions, you are guaranteed that the transaction will be finished eventually, and it makes life much easier. So now to the third step, load balancing. As I said, we are using we store the items directly on the ring without hashing, and you will get into situations where you have nodes which store more items than necessary, or nodes which have items which are more popular than other items. So there's a very simple algorithm for doing load balancing in these systems. It's two very simple steps. You pick two random nodes, you compare whether the load of one is higher than the other, and load in this case can mean whatever you want. You can define your load function in any way you want. You can take the capacity of the nodes into account and the popularity of items, whatever you want. So in this case, we assume that the node virt is overloaded, and we have a pairing of the nowa node and the virt node. And in this case, the nowa node will leave the system. The repair mechanism will repair this hole here. The nowa node will move here and join under a new identifier Tarjan, which will divide the load of the virt node into two equal sizes. And with this very simple local operation, you can adapt to basically every load imbalance. This is one point. The other point is, the Beamer has problems with gray tones. We can go to multi-data scenarios. For the Wikipedia, we have the keys of our system are the language, a colon, and the name of the page. And for the replication, we prefix these identifiers with 0, 1, 2, and so on, depending on how many replicas you want to have. So the German main page will end up with a replication factor of 5 in 5 places on the ring. And we can decide in our load balancing policy, well, in this area will be the third replica of every German page. It would be a good idea to have this interval stored on, let's say, in a British data center. So you can decide the German page will be accessed most often from Middle European countries or locations. So we want to have a few replicas nearby to reduce latency. So in this case, we can have 2 replicas in German data centers, 1 in the UK, and for failure resilience, 1 in the US and 1 in Asia. And again, for the next language, like Swedish, you can decide a different policy and have 2 replicas in, I don't know, Swedish data centers, and 1 in Europe, 1 Asia, and 1 in US. So you can, if you have a policy where to place your data, you can optimize for latency. Now to the final chapter everybody was waiting for, Wikipedia. When you go to Alexa, the top 10 web pages is this list. But we have a problem with 9 out of 10 because we don't get access to their data. We don't know what they are doing. Yeah, it's closed. So Wikipedia for us is the top 1 open website because we can get the source code. We can see which servers they are using, why they are using these servers, what the servers are doing, and we can get complete dumps of their data. And they also provide statistics about their usage. So this is a graph over, I don't know, 24 hours, how many requests they serve per second. So it went up to 50,000 requests per second. But what is most interesting for us is this black line at the bottom. These are the requests which went to the back end of the system. So 95% of the requests are served by caches. And we're not really interested in optimizing caches, but the back end is an interesting part for us. So we are only interested in these 5% of the requests. So this is a graph from the Wikipedia webpage. You can see how many web servers they are using, for what purposes. So in the front end, you have a couple of proxies. Some of them are in the US, some are in the Netherlands. You have a cluster of MySQL servers, and here you have a large group of HTTP servers which are doing the rendering. Now what we implemented, the core sharp, the load balancing, and the transaction framework are all implemented in Erlang. On the right-hand side, you can see the supervisor graph. So in Erlang, we have a lot of very small processes which are very lightweight and which are fulfilling exactly one task. You can think of it like objects in Java. So for each purpose, we have one process. And the supervisor tree will check that this process is still alive. For example, here we have a process which is doing failure detection. He's monitoring other core sharp nodes and checking whether they are still alive. And when the failure detector fails, the supervisor will immediately restart the process. And we get an error message that there was some bug in the failure detector, but it's still running, or it's running again. It's very helpful for debugging. And there's already implemented a distributed Erlang mode where you can have Erlang virtual machines running on several nodes in your cluster, and they will connect, and you can build your overlay. But there's some problems with security and scalability, so we had to implement our own layer based on TCP. Something I haven't told you: Wikipedia is using a SQL database, and you can use all this nice SQL stuff, creating tables, selecting and everything. But we have only a key value store. So you somehow have to map your SQL data, your SQL tables to key value pairs. So we have like one table for where we store the name. The name of the page is the key, and the value is a list of the versions. So when you want to know all versions of this article, you can look up under this key and get the list. You can create the diffs and so on, and get the complete history of this page. Another thing are categories. You can have an article on Washington and one on Berlin, and they will both have a tag that they belong to the category capitals. But again, if we only use this first structure for storing items, and you are asking me what pages belong to the category capitals, I have no idea. So again, you have to add a separate table, which is mapping the category name to the list of titles belonging to this category. And the same with backlinks. So if I want to know which other pages are pointing to this page, you have to add another table. So we're adding more redundancy, but we get to this key value database. So we're adding redundancy and storing items several times so that we can map it on a key value store. And so you can execute the transactions from Java. That's basically what the code looks like for updating a web page. You provide the title of the page, the old version number, and the new text of the page. You create a new transaction object, and everything from here to the commit will be executed inside of one transaction. You read the old page, check that the old page is still the old version you expected to have. If it's not, then there was a concurrent update, and you abort and retry. And otherwise, you can write the new version, update the category pages, and in the end, you say commit. There's a Java library called JInterface, which allows you to communicate from Java with Erlang processes. And that's what we are using for the transaction API. And yeah, that's basically the infrastructure we built on our cluster. You have a large core sharp ring for the database backend. You have a couple of web servers for rendering in the front, a load balancer, and then clients. So when a client makes a request, it goes to the load balancer to one of the web servers, and then the web server will execute this transaction. You make the lookup to all replicas, and you get the result back. You render the page, and the client eventually gets HTML code. We haven't implemented our own renderer. There was one in Flock4U. So the original one is in PHP, but yeah, Java was better in this case. And as I said, we are using JInterface to communicating between Erlang and Java. 3 weeks ago, there was the IEEE Scale Challenge in Lyon. And there we also had live demos. I'm not trying to do this today. We were using the Bavarian dump and a simple English dump, and had 2 deployments, one on a cluster in Berlin with 320 nodes for the core sharp overlay, and another one using PlanetLab. So most of the universities give 2 hosts to PlanetLab, and then you can go to PlanetLab and ask, I would like to have a machine in, I don't know, San Francisco, some in Japan, in Europe, and then you can run your experiments on this setup. When we are running it on PlanetLab, it's basically limited by latency, because when you make a request, when you are here and try to do try to read a page, and all the replicas are stored here and here, it's basically limited by the latency of the network. We were browsing was implemented, of course. You could edit pages and the category pages. Okay. The talk is had basically two parts. So we have this DHT with transactions, which allows us to have a nice scalable database. And then the Wikipedia was just one application we can implement on top. But it's nice because we get the data dumps from Wikipedia. There are probably a lot of other applications we can implement on top, but you have to be careful because you have to map it to the key value scheme. On the first page were mentioned me, Florian Schindke, and Alexander Reinfeldt, but there's a large group involved in this effort. We are collaborating with a couple of people from Stockholm. I know that it's supposed to be an industrial conference, but we also published the algorithms. And I'm basically ready for questions.